All right, let's start by talking about SSA. SSA is a situation where you know two sides of a triangle and you know an angle that's not included between them, such as the picture you see here. And SSA has some interesting outcomes because if one of the sides is too short, let's make this side 1. If this down here is locked in at a 40-degree angle and this side, say, is locked in at 6 centimeters, this short little 1 centimeter side, no matter what I do to this angle, is never going to create a triangle. So this is the 1, 6, 40-degree triangle is unbuildable, as an example. If this green side is too long, let's make this 9. Let me retrieve this here. Then there's only going to be one possible triangle because 9 is greater than 6, because you can make this triangle here with your 40-degree angle. But there's no way to swing this around to make a second triangle with a 9, 6, and a 40. So a 9, 6, and a 40 is a good example of a set of SSA numbers where you can only make one triangle. Well, we saw when this green side was too short or too long that we had a couple of different outcomes, but there's kind of a middle point. Here's the homework you had last week. You had a problem where this angle was 40, this side was 6, and this side was 4, and you had to go home and build a triangle. Well, you actually had to build two. If you built this one, then that would be one possible triangle. But with no restriction on this angle, in other words, since the 40 degrees or the known angle is not between the two known sides, that leaves the freedom to change this angle and make it smaller to the point where we have yet a second triangle that matches that. This is why SSA is not a proper triangle proof for congruence criteria, because if you know, for example, that a triangle has a 6 centimeter and a 4 centimeter side, along with a 40-degree angle not included between them, then there are two triangles, and we saw that here, that you could build. And if two triangles have these properties, they might be congruent or they might not be. So I would say those are three good examples of the SSA situation. Let's talk about angle, angle, angle. Angle, angle, angle. Let me move some things around here so we can see them better. Angle, angle, angle is an interesting scenario. If you know that you have two triangles, and they both have a 33-degree angle, and they both have a 40-degree angle, and they both have a 107-degree angle, you wouldn't necessarily be able to say they're congruent. I mean, right now you're looking at two triangles with those angles, and we have an angle, angle, angle situation, but the triangles clearly aren't congruent. And the idea with angle, angle, angle situations like this is you end up with similar triangles. Here you can see that one triangle is bigger than the other, but they're certainly not congruent just because the angles are congruent. Now let's say you had this side length of 6 and this side length was 9 for the bigger triangle. Then what you learned before in your similar triangles unit was that you could solve for sides based on other sides you know. For example, if I were to put a 5 here on a test and asked you to solve for x, then wouldn't you have set up the proportion 5 is to 6 as x is to 9 and solve for 9? By the way, the answer would end up being 7.5. So angle, angle, angle is a situation where you might not have two congruent triangles. In fact, usually you don't. But you do have similar triangles and they're solvable. You could solve this problem, for example. Before I move on to a new topic, though, one should be careful not to make triangles with more than 3 pieces of information. Because while this problem that you see in front of you may look to be solvable. And let's be clear, if I had put this on a test, most of you would have solved for x. You would have gotten, I think it's 7.5. You could do the math to check me. And you would have moved on with your life as if, okay, I've solved for x. But the truth, the secret truth behind these two problems is that these triangles don't even exist. I'll say more about that. Just looking at the triangle on the left, let's ignore the triangle on the right for the moment. The triangle on the left does not exist. Now, when you're looking at it, it seems to exist, but we could never physically create that triangle. Let's consider the 5, the 40, and the 6. We kind of have an side angle side situation here, don't we? Well, let's look what happens when we create a triangle with a 5, a 40, and a 6. Never mind the other two angles for a moment. Side angle side. If I want to make a triangle with a 5 and a 6 centimeter sides with a 40-degree angle in between them, I can definitely do that. Here it is. But what are these two angles? I have no idea. I mean, I could use my drawing program to measure them. Let's find out. Measure angle. Looks like it's about 84 degrees. That's fine. Let me get these labels out of here. They're annoying me. So this angle up here at the top is about 84 degrees. So we can definitely create a triangle with a 5, a 6, and an included angle of 40. But doesn't that prescription, those three numbers, doesn't that lock us into a unique triangle? And therefore, these two angles here are locked into whatever they are, like 84 degrees, for example. And if the 5, 6, and the 40 lock us into the other angles being whatever they are, then, let me go back to this other window. How could this angle up here be 107 if we drew the thing to scale? And the answer, of course, is that it couldn't be. And this is one of the dangers of having more than 3 pieces of information known on a triangle. And just on this one right here, we've got 5 pieces of information. If you put down 5 pieces of information, and typically 4 or more pieces, there's a really good chance that you're going to have a contradiction. There's a contradiction in here. This doesn't exist. I could make these sides 5 and 6, but that angle would be 84, as we saw earlier. Or if I made that angle 84, which is what it's supposed to be, then this angle would be something else. So you have to be careful when you put 4 or more pieces of information into a triangle, because it's likely that the random numbers you created for that represent something that's not physically buildable in the real world. So for this, and also while I'm on the subject of not having 3 pieces of information, what if we just had 2 pieces of information in a triangle? Say that one. Look at the triangle here on the left. If I just said, oh, let's solve a triangle where we have, what would we call this? Side angle or angle side? Well, this isn't really a solvable or interesting triangle either, because if you have too few pieces of information, say 2 pieces or even less, then there are going to be infinitely many triangles that can be buildable. So in summary, if you have 2 or less pieces of information, you probably have created a triangle that has infinitely many solutions, not of great interest to mathematicians. And if you have more than 3, for example, here on the left side of the screen, we have a angle side situation, then you've just created a triangle that doesn't exist, because as we saw on that other slide, this angle would have to be 84 for that to exist. So we don't much care for problems with 4 or more pieces of information because they lead to contradictions. And we don't much care about problems with 2 or less pieces of information because while there's almost never a contradiction, in fact, never, then we still are left with infinitely many triangles, and that's not a particular thing that geometers care much about. Okay, so What else should we talk about? I'm just mumbling to myself here. When it comes to these phrases like side angle side up here, what I just want to clarify what that actually means. Obviously, it means we know a side, we know an angle, and we know a side, but it means more than that. It can mean one of two things. It can mean we're given a side, an included angle, and a side, and we're being asked to find the remaining parts of the triangle. That, by the way, is something that you're going to do in IM3 next year. You'll see this problem or something like it next year, and someone will ask you, what's that angle, or what's this angle, or what's this side length over here? And we could find them if we were in an IM3 class, but I won't go down that road because we're not. But side angle side has another meaning, and you can't see it on the screen, but I'll describe it the best I can here in words. It refers to a situation where if we have two triangles with a matching pair of side angle side, in other words, if we had two triangles that both had 5, 40, and 6 in that order, these two triangles would be congruent. There'd only be really one triangle that can have those measurements. So when it comes to the acronyms like SAS, ASA, or SSS, those are theorems that are used to prove two triangles are congruent. Here's an example. We can build a triangle with side lengths 3, 4, and 6. Let me get rid of this here. We could build another triangle that had side lengths 3, 4, and 6, but guess what? Those two triangles would be identical, also known as congruent. So when we say side, 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 or any of these other acronyms, what we really mean is, given two triangles with matching side, side, sides, there's really only one such triangle that can exist, and therefore your two triangles are congruent. And again, in the IM3 sense for next year, but worth noting in your 7 questions, when we say we have a side, side, side situation, at least next year, that would mean that you are given 3 sides and you want to solve for the remaining 3 pieces of information, which in this case would be the angles. So lots to say about that, but let me move on. I want to talk about something you've heard me say in class, that angle, side angle, and angle, angle, side, while technically different, are fundamentally the same piece of information. For example, let me move some things around. This triangle here that you can see with the green, red, and blue, I would call that an angle, angle, side situation because the side we know is not between the two angles. By contrast, I would call this an angle, side, angle situation because the side we know is between the two angles. But the reason I say that these are effectively the same is, the minute you know two angles of a triangle, whether or not the side you know is between them or not, if we know that this is a 33-degree angle and that's a 67-degree angle, knowing that the angles of a triangle have to add up to 180, this thing would have to be an 80. Or let's say we change this to 90. Then that would shrink this angle down to 23. So knowing two angles of a triangle automatically tells you what the third angle is by the 180 rule. So the whole idea of, if you look up here at these two names, the whole idea of, well, do we know the side between the two angles, or do we know a side that's not between the two angles, is really a moot point, because the minute we have, let me give you this one, the minute we have a angle, angle, side situation, where the side we know that is not between the two known angles, well, we know the third angle automatically anyways, so the side we know is always between two known angles, because we know all 3 of them. So I don't really use angle, angle, side as a valuable tool, because every angle, angle, side situation is also an angle, side, angle situation. And what else should I mention here? Let's see. Let's look over each one of these things that lead to unique triangles, such as starting with side, angle, side, and then we'll do angle, side, angle, and then side, side, side. We'll do the first three here. And let's talk about physically why. Let me hide this thing here. Let's talk about physically why this leads to one unique, one and only one triangle. If you specify, oh, this side has to be 3, and this side has to be 7, and the angle between them has to be 100 degrees. The minute you've specified 2 side lengths and an angle, then this angle can't move. This point can't move because that side is locked in at whatever length you've given it. This point can't move because it's locked in by this length of, in this case, 7. So once you lock in those 3 parts of a triangle, the question of can we build this triangle, and if so, how many different ways, is yes, we can build it, and only one way. Because if that point can't move, and that point can't move, and this angle can't move, well then, there is your triangle. Change colors here. And you don't have any choice on how long that third side is going to be because it's prescribed or locked in by the blue, red, and black information. On to angle, side, angle. Let me get rid of this thing here. Why is it that when we know a side length is, say, 8, and we know an angle is, say, 42 degrees, and another angle is, say, 70 degrees, why is it that when we know 2 angles and the side in between them, that there's only one possible triangle that can be made with those specifications? Well, because the minute you lock in this side, you've essentially made these 2 points here immovable. And if you prescribe or lock in these 2 angles, which I have here, then the third point on your triangle has to be both on this green ray to maintain the 42 degree angle, but the other point on your triangle also has to be on the red ray to maintain the 70 degree angle. And since those angles aren't movable, and the third point on your triangle has to be on the green and red rays as you see them here, then guess what? That's where your third point of your triangle has to be. And that completes your triangle. And I won't draw it, but that, I hope you get the idea there. And finally, let's look at the side, side, side situation. In the side, side, side situation, there's no angles that are given. But let's say you say, all right, this side has to be 7, and this side has to be 4, and the remaining side, let me make this red, excuse me. Oops, I messed up something. There it is. And the remaining side has to be 3. Well, the minute you say what all the sides have to be, then you don't really have a lot of options. Now, the angles can move. In particular, this angle up here can move, but I'm not going to be able to make a triangle out of that. And if I make this long enough to reach, let's say I made this side length 5, then I should be able to make a triangle here. Yeah. Oh, something's gone wrong with my drawing program. Okay, let me see if I can fix it. Sorry, hold on. Maybe it's fixed now. No, it is not fixed. Let me just keep undoing here and see if I can get it back. I think this is how we started. Sorry for the downtime here. Let me change one of these and see if it works. Yep, something is wrong with my program, and I'm not going to sit here and bore you to death while I fix it, so I will simply try to do this problem in words without any diagrams. If you prescribe three sides of a triangle and you say, okay, I want to consider a triangle with side lengths 3, 4, and 6, then you can definitely build the triangle as you see it here. But once you pick all three sides, then you don't have any control over what the angles are going to be. Imagine that this green, the green, red, and blue sides were like toothpicks or some little physical objects that were unbendable. And someone handed you a toothpick with side length 3 centimeters, 4 centimeters, and 6 centimeters and said, here, make a triangle out of these. Well, you wouldn't have any control over what the angles would be. You would lay down those toothpicks. You'd make the exact same triangle, the only triangle that's buildable. And whatever the angles were, they'd be locked into position and you'd have no control over them. So that's the idea. Sorry for the lack of picture, and I hope this video helped.